of colloids. Very important. Colloidal particles exhibit colligative properties. So colligative properties means the property which depend upon only particles. Such kind of property is known as colligative property. For example, so I am taking one solution. Any one of the solution when you take it. So here I am adding 10 moles of NaCl salt. So 10 moles of NaCl salts, when I add it to this water, the sodium chloride will be dissolved. It means the salty nature, salty taste will be present in this solution, that is NaCl solution. Okay. Instead of 10 moles, I am adding 20 moles of NaCl. So 10 moles of NaCl solution, and when you observe the 20 moles of NaCl solution, which solution is high concentration? This solution is high concentration. High concentration, this is comparatively low concentration among these two. It means the concentration of solution is depending upon number of particles. Here 10 moles, here 20 moles. The property which depends on only number of particles. Here the concentration is depending upon number of particles. More amount of particles, more amount of moles are dissolved. Colligative property is more. Concentration is more. Okay. So when less moles are dissolved here, concentration will be less. It means whatever the property is depending upon the number of particles. Number of particles. The property which depends upon number of particles. Such kind of property is known as colligative property. So how many colligative properties are there we have means OP. OP means osmotic pressure. Delta P means relative lowering of vapor pressure. Delta TB means elevation in boiling point. Delta TF means depression in freezing point. So totally we have 1, 2, 3, 4 colligative properties regarding this. So clearly, total conceptually we are going to learn in solution chapter, but only one term you have to remember here. Colloidal particles influence colligative property. So in what way? The true solution osmotic pressure and as well as colloidal solution osmotic pressure, when you observe where the osmotic pressure of colloidal solution is less than true solution. When relative lowering of vapor pressure, true solution is high, and when you add colloidal particle to true solution, the lowering of vapor pressure will be less. Like that, freezing point also decreases when you add NaCl. That you know very well about that general example. The water, it will become cool after condensation, after freezing you will get a ice. When you add a little bit of salt, you will get a less time ice. It means freezing point will be decreases. True solution freezing point is somewhat high. When you add colloidal particles, the freezing point is decreased. So there is a comparison between true solution and colloidal solution. Whatever the concept, just leave it, concentrate here. Colligative property. Colloidal particles being bigger aggregates. Yes. The number of particles in colloidal solution is comparatively small as compared to the true solution at a given concentration. So here all the colligative properties are greater than with the colloidal solutions. Second point, optical properties. Colloidal particles exhibit optical properties. All colloidal solutions are capable of scattering light. Scattering light, when light is focused on a colloidal solution, the light will be Scattered. Scatters means spread entire available liquid. See here. Yeah, already is there here. This is the solution of true solution. Here the light is straightly going. But in case of you are seeing the light path. But in this case you can't see the light path. Entire light will be spread like this. When a light is focused on a colloidal particle, it will be spread like this. This is called scattering. Scattering means spreading here. All colloidal solutions capable of scattering the light. Because of this reason, scattering of a beam of light by a medium containing small suspended particles, which are colloidal particles. Example, smoke or dust in a room. When you observe early in the morning, when you open your window or door, the sun rays fall on into your house. At that time, you can observe the small dust particles or smoke particles, which are visible to light beam entering a window. This phenomenon is called as Tyndall effect. Observe here, students. Tyndall effect. Due to the Tyndall effect, the sky is looking like blue. Due to the Tyndall effect, sea also looking like blue. What is Tyndall effect? What are the influences? We are going to see some examples of Tyndall effect. Blue color of sky and sea, water. These are the exam due to Tyndall effect. Why? What happened? Actually, sun rays are coming from sun. So in between earth and as well as sun, we have a earth's atmosphere is there. In earth's atmosphere, we have a various dust particles, air particles are there, water droplets are there. When sun rays fall onto these all dust particles, means colloidal particles, which spread this sunrise, ultraviolet rays. Hence, we are looking like sky is blue. This phenomenon is known as Tyndall effect. Visibility of tails of comets. So, because of this reason, we are seeing this visibility. Twinkling of stars. Visibility of sharp ray of sunlight entering through the slit in dark room. So, we can see in dark room and at this situation, all rays we are seeing because of presence of colloidal particles. This phenomenon is known as Tyndall effect. Visibility of projector path and circus light. So, because of presence of colloidal particles, we are seeing sunrises, sky and sea is looking like blue. And eye, when you observe eye, here when sunlight is fall onto this eye, all rays will be spreading like this. So these are all the example for Tyndall effect. This is the optical activity of colloidal solution. Kinetic property. The continuous rapid zigzag movement executed by the colloidal particles liquid dispersion medium is called as Brownian motion. So when you observe a colloidal solution, any one of the colloidal solution, when you take any colloidal solution, what will happen? For example, gold small particles, when you dissolve in water, that gold particles will always move from one place to another place. The zigzag motion of particles. The random motion of particles here considered as a Brownian motion. The random motion of colloidal particles. A random motion comes under kinetic property. The continuous rapid zigzag movement executed by colloidal particles in a liquid. That liquid is, we are saying that dispersion medium is called Brownian motion. A colloidal particle in colloidal solution exhibits Brownian motion. This due to bombardment of particles dispersion medium on the particles of dispersion phase. Right? Here, in a solution, this is water, we are adding some colloidal particles. These colloidal particles will move zigzag motion. This zigzag motion only termed as Brownian motion. So these colloidal will be collide with each other, accident with each other, and colloidal particle may be collide with the walls of the container. During this also, the Brownian motion will be increased. A colloidal particles in a colloidal solution exhibits Brownian motion. This is due to the bombardment of particles of dispersion medium on the particles of dispersion phase. Smaller the size and lesser viscosity, faster is the motion of colloidal solution. Small size, definitely the motion will be fast and viscosity is less. Colloidal solution, a zigzag motion will be high. Brownian movement increases with rise in temperature. When temperature increases, particles movement also increases. So this is about the colloidal solution particles, zigzag motion. This is this direction, this direction, this direction. In any direction, all the direction, these particles are moving and bombarded with each other. When temperature increases, Brownian movement increases, and these particles will bombarded with colloid particle or colloid particle with water, that is dispersion medium. Next property, color. The color of colloidal solutions depend upon wavelength, light, scattering by the dispersed particles. The wavelength of light scattered further depends upon the size and nature of the particles. The color is depending on wavelength. Finest gold sol is red in color. As the size of particles increases, it appears purple, then blue, and finally golden color. Depends upon the size. When size increases, color is changing. See here, finest gold sol is red in color actually. As the size of particles increases, when you increase gradually the size of particle, the color is slightly changing. First appears purple, then blue, and finally golden color. Electrical property. We know that all colloidal particles exhibits either positive charge or negative charge. Negatively charged colloidal particles we can termed as ionic surfactants, anionic surfactants, and positively charged colloidal particles we can say that cationic surfactants. Because of presence of positive ion and negative ion, definitely they conduct electricity. So this is about the missile formation. This is anionic surfactants. When dissolved in water, it forms ions. When it forms ions, it is responsible for the conductance, electric conductance. Cationic surfactants, example, cetyl triammonium bromide and cetyl triammonium chloride are the example for cationic surfactants. One more property, some important terms. Each sol particle is surrounded by the either positive or negative ions in the form of fixed layer or compact layer. The second layer is diffuse or mobile layer consisting of ions which charged being equal. The potential difference developed between two layers is known as zeta potential or electrical kinetic potential. Important point, zeta potential. Zeta potential means, so here for example we are going to prepare a colloidal solution. Oil in water, that you know. Water one layer and oil one layer. So two layers. So this is the viscosity. What I said in the first point, each sol particle is surrounded by either positive or negatively ions in the form of fixed layers or compact layer. The second layer is diffuse or mobile layer consisting of ions which is charged being equal. This is the second layer which is float on this layer. This point, the potential difference between the two layers, this layer and this layer, is known as zeta potential or electrical kinetic potential. The existence of charge on colloidal particles is confirmed by electrophoresis experiment. What is the charge? Either positive charge is there on colloidal particle or negative charge is there on colloidal particle. That is experimentally proved, which by the experiment is electrophoresis experiment. The movement of Sol means colloidal particles under an applied electric potential is called as electrophoresis. Due to the presence of electric current, the colloidal particles move from one place to another place. This phenomenon is known as electrophoresis. The movement of the dispersion medium under the influence of applied electric current potential is known as electroosmosis. Here, dispersed phase particles are moving. Here what will happen? Dispersion medium is influencing. When dispersion medium is influenced with the applying of electric current, that is electroosmosis. When dispersed phase particles are influenced by the electric current, that is called as electrophoresis. So these are the important terms related to the properties of colloidal solutions. Now the last part in this chapter, part 5, stability of salts. In what way these colloidal solutions are going to stable? Coagulation or precipitation or colloidal solution. Coagulation means clotting. So for example, see here, this is one of the solution. Solutions, already I told you, two different important kinds, which are lyophilic and lyophobic. Lyophilic and lyophobic. Actually, Leo, instead of Leo, Lyo is the correct pronunciation. Lyophilic and lyophobic colloidal solutions. Lyophobic means, for example, we have two layers. Okay, so this is water. This is small gold particles. Okay, gold particles. Small gold particles. So lyophilic means both attract each other. For example, starch with water. Now I am going to explain you. When starch with water, when you dissolve starch, simply warming it, heat it at 100 degree centigrade temperature, starch and water are miscible with each other, you will get a colloidal solution. So this is starch colloidal solution, is example for lyophilic. Right? Then this is gold particles. When you place it in the water and shake well, mix well the solute and solvent, then you will get a gold sol or gold colloidal solution. This is lyophobic. This is phobic. When you kept few hours, all gold particles will be formed at the bottom. They are clustering, the togetherly forming. This clotting of gold particle, the aggregation of gold particle together. So this phenomenon is known as coagulation. That is called precipitation. So that precipitation you cannot observe in lyophilic. That precipitation you can observe in lyophobic. This is coagulation. This will not undergo coagulation. Lyophobic colloidal solutions undergoes coagulation. In what way it will undergo, we will see one by one. Protection of colloids. So how to protect from coagulation? So gold sol is there. That should be uniformly, all gold particles should be distributed in water. That should not be come under the container. So how to do that? That is called a protection of colloids. Application of colloids in our daily life. And what are emulsions? Characteristics of emulsions. Applications of emulsions. These topics we are going to see. one by one. Let us go for stability, and last topic is gel. Stability of salts. The presence of equal and similar charges on colloidal particles is largely responsible in providing stability of the colloidal solutions, because the same charge prevents the form of coalescing or aggregation when they come closer to one another. The presence of equal and similar charges. If any colloidal solution, when you take it in a container, for example, that colloidal solution, you know about soap solution. Soap particles have a minus head is there. This is carbon tail. So negatively charged particles all will be formed in the colloidal solution. One particle is repelled by another particle. One negatively charged particle is repelled by another negative charged particle. So there is no possibility to gather or no possibility to form at one place. They should not be touched with each other because same charge is there. So that they won't form in the bottom like gold particles. That point is explaining. The presence of equal, same and similar charges on colloidal particles is largely responsible in providing stability. Same charge, equal quantity, same number of molecules are there. Hence, they are more stable. Colloidal solution is more stable. It will not clot. Example, see here. Example of stable colloid. These are the examples of unstable colloid. These are clustering forming. All colloidal particles are formed as an aggregation. Sedimentation. They are all formed at the bottom. So this is unstable, but this is stable because presence of negatively charged colloids. Coagulation or precipitation. First one, stability is over, and how the colloidal solutions are undergoes coagulated. The stability of leophobic salts is due to the presence of charge on colloidal particles. If somehow the charge is removed, the particles will come near to each other to form aggregates and settle down under the force of gravity. If charge is there, okay. When you remove the charge, same way, all the particles will come and stored at the bottom of the container. All colloidal particles are stored at the bottom of the container. So this is water. These are the colloidal particles. So this process name is known as what? Coagulation. The process of settling of colloidal particles is called as coagulation or precipitation. The process of settling of colloidal particles is called as settling down at the container is known as precipitation or coagulation. A colloidal solution can be coagulated by the adding of electrolyte. So when you want to coagulate a colloidal solution, you want to add an electrolyte. For example, this is another colloidal solution. Another colloidal solution. So all the colloidal particles are distributed uniformly in the space of the water. These are all colloidal particles. So this is stable. When you add an electrolyte, what you are adding? Electrolyte. Electrolyte means NaCl, ionic compound. When you add a little NaCl solution or 1 ml, 1 milliliter solution, one drop you are adding, what will happen? When you add one drop of electrolyte to the colloidal solution, all colloidal particles are settling down. All colloidal particles are settling down. This settling down of colloidal particles at the bottom of the container only known as what? Coagulation. So above that we have water molecules. But that is the point. A colloidal solution can be coagulated by the addition of electrolyte. By the addition of electrolyte you are getting coagulated. Precipitate you are getting. Precipitate you are getting. When you want to coagulate, when you want to separate your colloidal particles, you have to add what you want to add? Electrolyte. When you add, the colloidal particles will be separate out, coagulated. It means they formed at one bottom. To prevent this coagulation, what you want to do? The ion which is responsible for coagulation of colloidal solution is known as effective ion. Now I added NaCl, you know that ions are called effective ions. The effective ions of an ion or electrolyte in causing coagulation depend on the charge or sign and charge magnitude. This fact is initiated by Hardy and Squeeze rules. So when we add electrolyte, the stable colloidal solution is getting coagulated. In what way it will be coagulated? Two scientists explained in the following manner. See here. Hardy and Squeeze rule. The ion which charged opposite to the charge of colloidal particle is effective in coagulation or coagulating the colloid. For example, colloidal solution where the colloidal particles are negatively charged. When you add positive charge electrolyte, what will happen? This positive charge electrolyte will attract this negative, then all will be gathered again. So this process is coagulation by using of opposite terminals. Second point. Greater the charge of ion, greater is the coagulation ability of the ion. If this charge, whatever the electrolyte charge is high, for example, aluminium charge is high, Al plus 3. Sodium charge is less, Na plus. So this is the high charge. Instead of sodium, when you add aluminium, what happened? The coagulation process will be greater in this solution, comparing with this solution. Positive colloids are coagulated by negative ions or anions of the salt added. Coagulation ability is in the following order. FeCN taken 6,4, ferrocyanide ion, phosphate ion, sulfate ion and chloride ion, where this coordinate complex ion is having high coagulated capacity. Negative colloids are coagulated by positive ions or cations of the salt added. Coagulation ability is in the following order. Aluminium ion is greater than barium and plus. Charges are here plus, plus 2, plus 1. Here charges what happened? Minus 4, minus 3, minus 2. This is minus 1. Flocculation value. Flocculation value or coagulation value. Another name is precipitation value. It is the minimum amount of electrolyte in millimoles that must be added to 1 liter of colloidal solution to bring about complete coagulation or precipitation. So coagulation means what I told you? Cluster forming. All colloidal particles are come down the bottom of the container when you add a electrolyte. So total colloidal particles all are comes down. That value at how much quantity when you add to get all colloidal particles at the bottom, that quantity value is considered as flocculation value or coagulation value. Coagulating power is inversely proportional to flocculation value. When coagulation is increases, flocculation value decreases. The relative coagulation power of two electrolytes for the same colloidal salt, when we have the relation is there for mathematical calculation, coagulation power of electrolyte 1 divided by coagulation power of electrolyte 2 is equal to coagulation power of electrolyte 2 divided by coagulation power of electrolyte 1. Just E1 by E2 is equal to E2 by E1. Coagulation can also be caused by the electrophoresis. Electrophoresis means while sending the electric current, all the colloidal particles will be come down. So mutual precipitation, mixing of colloidal salts are opposite charges. Prolonged dialysis are by heating or cooling the salt. Coagulation, we can done these three important methods. One is electrophoresis. The second one is prolonged dialysis or heating or cooling. These are the methods to follow colloidal particles are settled down. Protection of colloid, very important. Leophobic salts are less stable than leophilic colloids. That already I told you. Leophilic are more stable. Colloidal particle and dispersion medium particle will not separate because affection is high. But leophobic colloidal solutions, the interaction is very less. Hence, this is less stable. A leophobic salt can protected from coagulation by adding leophobic colloid. Very important point, my dear students. As per the classification, how many types of colloidal solutions we have? Two, leophilic, leophobic. Leophilic and leophobic. So leophilic means the interaction is high between these are the colloidal particles. Interaction is high. But leophobic, we have a less interaction. We have a very less interaction. Almost all repelled each other. Because of this reason, when you mix it, the gold particles is mixed up. When you keep a 5 to 10 minutes, all particles will be formed at the bottom. That is the reason leophobic colloidal solutions are less stable. Leophilic colloidal solutions are more stable. More stable. The leophilic salts added to protect the colloidal solution. Now see here. All colloidal particles are settling down. To prevent this, this is the water. To prevent this, we have to add leophobic compound. Leophilic compound. This solution is what? Leophobic. So leophobic is less stable because all colloidal particles are settling down. To prevent this settling down only our chemistry term coagulation. To prevent this coagulation, what we have to add? Some little quantity of leophilic colloidal particles we have to add. The leophilic salt added is called protective colloid. When you add leophilic salt to this leophobic, then colloidal particles will not come down. Such kind of solution is known as protective colloid. This is protective colloid. Because the settling down is prevented by adding of leophilic. This process is protective colloid. So to stabilize the leophobic colloidal solution, you have to add a protective colloid, that is leophilic. Zsigmondy introduced the term gold number. Measure the protective power of different colloids. The number of milligrams of protective colloid which is just sufficient to prevent the coagulation of 10 ml of standard solution of gold solution when 1 ml of 10% of solution of sodium chloride is added to it. It is called a gold number. So very important definition, one more is coming here, gold number. Gold number means, see here, now I am preparing one solution. Observe carefully, most of the students will confuse to calculate the gold number. See here, this is one of the solution. 10% NaOH solution it is. 10% NaCl solution. What is the meaning? It means 10 grams, 10 milligrams or 10 grams dissolved in 100 ml of the solution. 100 ml of the solution, that is a 10% solution. And now this is weight volume solution, weight volume type of solution. This is 10% NaOH, 10 grams of NaCl. 10 grams of NaCl dissolved in 100 ml of solution. Okay. Now in second way, I am preparing lyophobic solution. Lyophobic solution means inside we have a gold particles, gold and this is water. Gold means gold particles now. This is lyophobic. Okay. Now, in what way I am going to calculate the gold number? All of you observe carefully. Lyophobic solution means after 5 or 10 minutes, all gold particles will be come and settle down. So, I want to do without settling I want to prevent the settling. I want to prevent the coagulation by adding third material. This third material is known as what? Lyophilic. A little quantity you have to add. So this third particle, third material I have to add. This third material when I add, what will happen? To prevent the coagulation, these colloidal particles will not settle down. So now coming to for example, 0.1 milligram I added. One third compound. 0.1 mg of a component when added to the lyophobic solution, colloidal particles will not settle down at the bottom of the container. So hence this is called as a protective colloid. Clear? The number of milligrams of protective colloid, 0.1 mg I am adding. Protective colloid, which is just sufficient to prevent the coagulation, to prevent the clotting of 10 ml of standard gold solution. This is how many milliliters? 10 ml of solution, gold solution. Now, when 1 ml of 10% of solution, sodium hydroxide or sodium chloride solution is added to it. What is the meaning of this? Up to here you understand. The number of milligrams of protective colloid is just sufficient to prevent the coagulation of 10 ml of standard gold solution. How much amount of quantity is minimum quantity is required to prevent the coagulation? That minimum number of milligrams is known as gold number. When 1 ml of 10% of solution is added to sodium chloride is added to it. See here, before I prepared this 10% of NaCl solution. This side I have prepared 10% of NaCl solution. From this I am taking 1 ml. How many milliliters? Here 1 ml I mentioned, 1. So 1 milliliter, 1 drop, 1 ml I am adding to this. Before adding of this 0.1 mg, when you add 1 ml of NaCl, all colloidal particles will be settling down, coagulated, right? I tested. Okay. Now I added what? 0.1 mg of leophobic colloid I added to this. Still I am going to checking it. When I add 1 ml of NaCl to this solution, even though these colloidal particles will not settle down. We are cross checking with 1 milliliter of 10% of NaCl solution. Is it coagulated or not? Is testing with this. So finally I am going to tell you the definition. The number of milligrams of protective colloid which is just sufficient to prevent the coagulation of 10 ml of standard gold solution. To prevent the coagulation, how much milligrams you are going to add it? That is called as gold number. When 1 ml of 10% sodium solution of sodium chloride is added to it. Even when you testing with 1 milliliter NaCl solution, when you test it, these will not settle down, isn't it? So this is about the gold number. When you won't add more quantity, that is the reason here they mentioned 1 ml of 10% solution, you can check with. So each and every protective colloid have a fixed number. I am going to give the list. Gelatin is 0.005 to 0.01 milligrams. When you add it, the colloidal solution will be settled. It will not coagulate it. Hemoglobin is also considered as a protective colloid. Then you can add 0.03 to 0.07. That is the reason our blood is also going to clot when you keep it in outside. Casein 0.01 to 0.02, albumin 0.1 to 0.2, and gum arabic is 0.15 to 0.25, potash starch is 25. Number is the gold number. Milligrams, all are expressed in milligrams. So I am giving one mathematical relation. Protective power, they are all protective colloids. This protective power is inversely proportional to gold number. When gold number is 25, protective power what happened? Decreases. When gold number decreases, protective power increases. So based upon the gold number, which colloidal solution have more protective power, we can decide it. This is about the protection of colloid by adding leophilic colloids to leophobic colloids. Applications of colloids. It is used in purification of drinking water, electric precipitation of smoke, Cottrell's precipitator. Smoke carry negative charge and is removed by the principles of electrophoresis in Cottrell's precipitator. Artificial rains. There also we are applying this colloidal solution process. And sewage disposal, electroplating of rubber, lathering, tanning, and photographic plate and films. Last topic is emulsion. When both the colloidal particles, dispersed phase and dispersion medium, both are existing liquid state, such kind of colloidal solutions are known as emulsions. Dispersed phase and dispersion medium both will be in the liquid state. Oil and water. Water and oil. Oil in water type of emulsion, water in oil type of emulsion. Your dispersed phase is oil. When dispersion phase is water, where you change different types of two kinds of emulsions, you are going to get it. The dispersion of finely divided liquid droplets in immiscible liquid dispersion medium is defined as emulsion. Generally in emulsions, one of the liquid is water and another is a immiscible liquid, generally that is oil. These are the examples for emulsions. We have two types, oil in water type of emulsion, water in oil type of emulsion. The stabilizes an emulsion the addition of small quantity of third substance known as emulsifying agent. Here third substance we are going to add to stabilize. So for example, oil in water, while mixed vigorously you will get a emulsion, oil in water type of emulsion. When you keep aside for few hours, oil layer will separate out from the water. So you won't get it from oil layer separate from water, you have to add third substance. That third substance name is termed as emulsifier. To stabilize the emulsion, the addition of small quantity of third substance is known as emulsifying agent or emulsifier is essential. For example, kerosene in water, when you add soap, so kerosene and water, two layers will not separate it. So that here soap is called as emulsifier. Olive oil in water, where egg albumin act as emulsifier. Water in benzene, solid HgI2 acting as an emulsifier. Milk, when you add casein, where this is acting as an milk, how it will form fat and water. So without separating, when you want to won't separate it, you have to add casein. Ice cream, so gelatin you have to add it. So this is about the oil and water do not mix. This is oil layer and water layer. Oil in water emulsion. So by mixing these two, when you have to add some third substance. Water in oil type of emulsion. Characteristics of emulsion: appearance, emulsifier, dilution, spreading, viscosity and dye test. These are the properties. We'll see one by one. Oil in water type of solution, we have water in oil type of emulsion. Appearance, when you case W by O, W by O means O by W, oil in water. Water opaque and translucent, oil opaque and translucent. Emulsifier, what is emulsifier we are using to use here? Water soluble substance. Here the emulsifier is oil soluble substance. Dilution, when you add water, water added is soluble but not oil. Oil added is soluble but not water. When you add oil, oil only soluble. When you add water, here water only soluble. Spreading, spreads easily on water surface, spreads easily on oil surface. Viscosity, a little more than water, more than water. Dye test, a water soluble dye gives uniform colored background when added. When you add dye to this, an oily soluble dye gives uniform colored background when added it. Water soluble oil, when you add, the water will be get color. Oil soluble dye, when you add, oil going to get the color. Applications of emulsions: in washing process of clothes and crockery, in the digestion of fats in the intestines, as a lotions, creams and ointments, in pharmaceuticals and cosmetics we are using all emulsions. In the metallurgy, concentration of ore is carried out through the emulsification. In the conversion of cream into butter, by churning this breaking of emulsion of fats into water. In natural oil wells, oils and water form emulsions, hence de-emulsification is necessary. In natural oil wells, oil and water both we are collecting. From that, what we have to do is water we have to separate from oil. So that is called as de-emulsification. De-emulsification means the breaking of an emulsion into aqueous and non-aqueous phases. Oil is non-aqueous, water is aqueous. We have to break down to separate layers. An emulsion can be de-emulsified by the physical methods like freezing, boiling or centrifuging. So freezing, among any one of the component, one component have less freezing point, that will be freeze it. Boiling, any one of the compound in oil and water, one should have more boiling point, one should have less boiling point. First one component will boil, another one we can separate easily. Same way centrifugation, you go for milk, when you centrify it, all fat will be come down and water will be above the centrifugate. Centrifugation of milk providing the amount of fat and water. Finally, gels. A gel is a colloidal system in which liquid dispersed phase in a solid. Both are liquid, that is called as emulsion. But here liquid dispersed phase in solid. Dispersed phase is liquid. Medium is solid. That is called a gel. I am giving few examples for gel. The common examples of gels are gum arabic, gelatin, processed cheese, silica, silicic acid, and ferric hydroxide. Gels may be classified in two types: elastic gels, gelatin, agar-agar, starch; non-gelatin gels, silica gel. Few differences we are going to learn about the elastic gels and non-elastic gels. Possess electricity, does not possess electricity. They readily change their shape on applying force and return to the original shape when the applied force is removed. They are rigid. They change it to solid mass and dehydration, which can be changed to original form by addition of water followed by the warming. Same way, they change it to solid mass on dehydration, which cannot be changed back to original form by addition of water and warming. They absorb water when placed in it within simultaneously swelling to get body. This phenomenon is called imbibition, but in imbibition process non-elastic gels will not